Workplace 10. Drawing similar polygons. Now, polygons are just shapes with many sides. Smallest amount of sides you can have is a triangle for a shape, two-dimensional shape, right? You can have 17 sides, you can have a billion sides. Now, working with scale diagrams. We're going to be using the same skills we've always had, but we're going to be using our rulers too. Let's listen here. Artists, architects, planners use scale diagrams or models in their work. The diagrams or models should be in proportion to the actual objects so that others can visualize what they look like. We're going to practice drawing scale diagrams. A fairly simple diagram here. Use graph paper, which I've given, to construct a figure similar to the one given. The sides are 1.5 times the length of the original. And how will you know that the corresponding angles are equal? Well, what do we know from the, as far as we can answer that angles equal thing right off the bat. How the angles are equal? Well, it doesn't necessarily have to be 90. One of them is 90, this one is 90. But what do you know about similar shapes? If they are two triangles, for example, that are similar, what do you know about all their angles? They're all equal. It doesn't matter if you've doubled it or tripled it. Right away, let's just jot this down. Corresponding sides will be in proportion. So we say corresponding, that means matching, but it's a good math word. Corresponding sides will be in proportion. That means exactly twice as much or 3 times as much. In this case, 1.5 times. Proportion, so that's the math word. So if that's the case from our previous section, that means that corresponding angles will be equal. So, corresponding, that means matching. Angles will be equal. Now we know all the angles in the new shape will be the same. That's what that's from. And we'll think about this problem before we draw it, and then we'll draw it. What I need you guys to do after you copy that out is to count how many squares it goes this way. We'll do the straight sides. How many squares it goes this way. How many squares it goes this way. And we'll talk about how many squares it goes up and then over. You can't really count the diagonals as easy. Sometimes, actually this one you could, but it makes it easier if you don't count on the diagonals. You just count the straight up and over. The slope we talked about. So I'll give you guys a second here. 12 going up. I'm talking here. You're counting the whole thing. I know what you're doing. So that's just a plain old, it's a 6er, ain't it? And this one on the bottom, now I'm sure you can count this in a jiffy, it's 4. At the bottom line, come on, Brooklyn. You can do it. You got it, right, Misha? What? The bottom is 18? Good.
Yeah, it's 18.
You know what we're doing though, right?
Got it.
Don't be asleep on it. Now, like I said, the diagonals, it gets tricky. Now this one you can count because it actually cuts through squares perfectly diagonal. But we should always count how much up and over it is. So I'm going to draw a dotted line. That's up 4 and over 4. That's the diagonal that we're going to use to find where the diagonal ends. Up 4, over 4. The other one, as long as we draw this line here and this line here, we can just join the dots for the last one. We could do the up and over for that one too, but we'll see. I think we should be fine with this. Now, the new drawing on the bottom, 1.5 times the length of the original. So you're gonna have to multiply each one of these by 1.5. So what we're gonna say is, let's start with the bottom line, the big one. 18 times 1.5 on your calculator if you can't do it in your head. Calculator. $1.5 is 1.5. So just scooch that up a little bit so I can write myself. So this one is 18 times 1.5, which is equal to, Tori has my answer, right? 27. So with your ruler, I would start at this corner right here and draw 27 over, okay? So count it careful. There you are. Just count myself. I'm going to draw from there to there with the ruler. Luckily, I have straight lines here. A lot of this down so it doesn't move on me. Okay. On the other side, so you're doing this, right, Tori? Okay. Instead of 6, I'm going to go 6 times 1.5. Which is equal to, figure that, 9 it is. You take 1, 6, and then half of that, plus 3. So up 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. I'm going to draw my straight line. Great. Now, to do the diagonal, I am going to go with, remember how the diagonal is up 4 over 4, like right here? We're going to count, but instead of 4, you know, we're going to go 4 times 1.5. 6. So that's 6. Awesome. So what I'm going to do is, I'm going to start, and just put the dot here. I'm going to go up 6 over 6. Why 6? Because here I went up 4 over 4 and I multiplied 4 by 1.5. That's 6. That's what I'm figuring out here. So I'm going to go, oh, there's my dot. I'm just trying to get, there we go. There we go. Up 1, 2, 3, 4, 5, 6 over 1, 2, 3, 4, 5, 6. So what I just did was, and you guys, you don't make marks there, but you count up 1, 2, 3, 4, 5, 6, and over 1, 2, 3, 4, 5, 6. Place your dot there, and then connect your lines, because that will give you the piece that's proportional to this one, right? Up 4 over 4, up 6 over 6. So that's what you see. I heard you say that. I see. It's good. Okay. And it should hit all of those lines right on their corners, or all those squares, like right on these corners if you did it correctly. Okay. And then the top line. That was over 4 as well. We already worked out what 4 times 1.5 is. It's 6. So you're going to go, move it over, 1, 2, 3, 4, 5, 6. Going to draw your line in there. And the last one, right? 6 on that one. We figured that one out basically on the side. It's the same. It was over 4 in the original. It's over 6 in this one. You see that? We never did any figuring for this line here, right? But as long as we have this end correct here, and this end correct here, as long as we join the dots, we're good, right? It'll be 1.5 times larger. So you're going to join this dot to this dot using a straight line. This is exactly where I hope you're using rulers, yeah. Oh, yeah. Don't freehand this one. Okay? Everything. You just groove. Now, hopefully your drawing looks something like that too. So, last ones, I'm just waiting for you, and then we'll get cracking on another example. Okay, Satori, you're done. Misha, you're just about done. You messed up? Mess up, Buttercup. Good thing you noticed it, though. Okay, so we will flip the page in a second. If you have a little more to connect and stuff after this, Misha, you're good now? You can come back to it after, though. Okay, I'll help you out if you need. So, let's look at the next page. Xavier. Drake is building a staircase using scale drawings. On the drawing, we don't see the drawing, but we can still understand this. The height of one stair is 0.5 centimeter, and the depth is 0.9. The amount it goes down. The height, or I mean the amount it goes sideways, the depth, 0.9. Xavier will use a scale factor of 40 to build his stairs. Calculate the height and the depth of the stairs he will build. Now, you could do this a number of ways. You could just think it through. If you understand scale factor and say, just multiply by 40, that's great. If you're tricked out by this and you say scale factor of 40, would 40 represent the big real life stairs, or would it represent the small drawing? I would hope the 40 is the big, right? The real life stairs. So if you want to, you can just say, well, the stairs and the drawing. Stairs and drawing. Well, the stairs are 40 for every 1 centimeter on the 40 centimeters for every 1 centimeter on the drawing, right? That means it's a 40-to-1 scale factor. Now, like I said, if you're a sharp cookie with this stuff, you could just think, oh yeah, I'm just going to multiply. But if you're not, it's fine. You'd say, well, if the stairs are 40 for every 1 centimeter on the drawing, and my first thing, the height of the stair, is 0.5 centimeter. Where am I going to put that, Brooklyn? Where would I put half a centimeter from the drawing on this fraction here? Top or bottom? Bottom, of course, because that matches that. So you're going to put that there. I'm going to say 0.5 centimeters here. And let's call it the height, so it's h.
20.
Whew, 20. Half of 40 is 20. 20 centimeters in height. Likewise, same scale factor. It's a 40 for the stairs, 1 for the drawing. But this time we're talking about the depth of the stairs. So it's the same thing, decimal 9 centimeters. For the D, depth. And 36 it is. Okay. Now, you guys are going to try some more problems right off the bat. What you're going to do is, this first question is very similar to this. Scale ratio, model to original. I'd use a fraction though, 3 to 5. So I'd say the model is 3 and the original is 5, and that's equal to something. You'd figure that out, okay? What was the measure on the original? This one here, draw a rectangular prism. Use your ruler. The sides that are half their original. So you're thinking, for example, this side, it won't be 8. It'll be 4. It's half. You can do half of it. 2 will be 1. The 3, 1.5 centimeters. You guys got rulers, so that's good. You're going to draw it neatly. Draw the front, I would suggest, first. And then do your best to draw the other 3D portions. Right? Then, this cruise ship one. You could try that. It's more of those setup fractions. Okay. You guys should be able to do that. I'll stop recording. And if you were stumped on something, I'll come around in a second here. I'll just stop the recording. Stop sharing, because I hate sharing.